So we will be talking about electrical systems. By themselves, for us, electrical systems might not be too important, but electromechanical systems are. So, as you all know from other courses, what are the elements of electrical systems? Let's briefly talk about these. You have the basic element is the resistor R, where if there is a voltage difference between here and if there is a current going through, let's say let's say that there is a voltage difference. The defining equation is, as you know, is the Ohm's law, which is V equals Ri. You might have the capacitor, which stores electrical energy, C, let's say. This is the voltage difference. Let's call this VR, by the way. VC would be equal to, sorry, we cannot say VC. This is VR. This is the current that goes through here again, I. The current is proportional to the rate of change of the voltage across it. Okay. As you know, this stores electrical energy, and there is also the inductor, which stores magnetic energy, L. The current is here, and the voltage drop here is proportional to VT. These are the basic passive electrical elements. And you also have electrical sources, as you know. There is the voltage source, ES. It can be a DC or AC source, in which the voltage characteristic is equal to Vs. And you might have a current source as well, as you know. This is shown by this. Here, the current that goes through it is equal to the source current. Okay. These are the basic elements of electrical systems. There are others, of course. There are things like diodes, transistors, and so on, but they are a matter of electronics, not of electricity per se. In the linear electricity, these are the elements we deal with. And in order to deal with these things, we have the certain laws, basically Kirchhoff's laws, which are conservation laws, which says that sum of voltages so if you have a path like this, let's say this is V1, this is V2, this is V3, let's say. Basically, it says that the voltage drops, let's say, let's show currents like this, okay? For example, it says the following trivial thing, actually. There is a voltage drop of V3 minus V1 here in the first thing. Let's say this is 1, this is 2, and this is 3. Okay, V3 minus V1. Then this thing is plus V1 minus V2, which is V2, right? Which is V2, plus V2 minus V3 adds up to 0. And you see that they cancel each other. You can write this as, if you like, V1 plus V2 plus V3. 3, 0. Okay. This is what KVL says, actually, nothing too extraordinary, as you see. Kirchhoff's current law, KCL, states that sum of currents to a junction, let's say, equals 0. Basically, if you have a junction like this, you have, let's say this is I1 coming in, I2 going out, and I3 going out. It basically says something like I1 equals I2, or I should say I1. I1 comes in, so it's a positive, minus I2, it leaves, minus I3 equals 0. Okay? Something like this. It's quite easy to understand. It is conservation of charge. The other is the compatibility equation, the voltages, the KVL. We use this to derive the equations for the electrical systems. We use these laws and the elemental equations. These are the equations that describe the system. Okay, these ones are the okay. It came out to be okay. The equations in the box plus KCL and KVL allow us to derive the equations and differential equations that describe a system. For example, a very basic electrical system is the RC circuit, which is the following. There is a resistance and a capacitor. This is the input voltage. Let's say we call it EI. This is input to the system. This is R. This is C. And then the voltage across the capacitor is VO, which is the output. So output is the capacitor voltage. Input is the voltage to the voltage input, let's say, to the resistor. And this part might be grounded, let's say, the bottom part. We would like to obtain the relationship between the input voltage and the output voltage. And also there is a current that goes through this circuit. We call it I. Now, KVL says that the voltage supplied is equal to the voltage dropped. So it says that VI is equal to VR plus voltage across the capacitor. Okay. The voltage across the capacitor, what is that? The VC is here. dVC dt is equal to I. So, as you know, I is equal to C dVC dt. From which you can say that we can integrate this equation to be VC is equal to 1 over C integral 0 to T of I dt. Okay. And we know that VR is equal to IR, so VI is equal to IR plus VC is this 1 over C integral 0 to T of dt. Okay. Well, this is the kind of the equation that describes the system, but we would like to get rid of the I term if possible. Okay, that is the, well, that's our aim. The I term is an intermediary, and we would really like to express everything in terms of VO, not VI. And as a matter of fact, VO is equal to VC, which is the voltage across the capacitor. This is the output. But how do we do it? You can deal with it with taking derivatives and so on, but it is easier if you just convert everything to use Laplace transforms. Use Laplace transforms, let's say. Because you convert everything to algebraic equations now. IR, like R, I is the converted plus. Now, integral. You have the integral. Integral of a Laplace transform of the integral, as you might remember, is 1 over S. Differentiation is S, and the integration is 1 over S. So it is 1 over CS times I, which we can write as, factor it in 1 plus CS I. Okay. On the other hand, VO was VC, as you know, which is again I over CS, right? CS. So we can say that the transfer function, that is the output voltage divided by the input voltage, which is output divided by the input. VO over VI is, VO is I over CS, yes, divided by this, which is VI. There are other ways to get rid of this I term. That's all I'm doing here. Okay. As you see, I terms cancel from here. We get 1 over CS divided by R plus 1 over CS. I can write this as 1 over CS divided by, okay, let's write it, 1 over CS divided by RCS plus 1 divided by CS, and these C to S terms cancel. And finally, we get the output voltage divided by the input voltage as a simple expression, which is 1 over RCS plus 1. This is a plus. Okay. This is the Laplace transform, the transfer function of this system that relates to the output voltage to the input voltage. If you want to obtain the differential equation, this reads like the following: RCS plus 1 times V0, V naught of S, VO, is equal to VI of S, okay? And since you remember that S represents d by dt, the time equation would be RC dVO dt plus VO is equal to VI of t. This is the differential equation. differential equation representing the system. Okay. There is only one parameter in the differential equation. Not well, there are two, but one thing, that is the multiplication of R and C, gives you the, as we will see, it is called the time constant of this system. So this is the equation that describes this system, for example. It is a first order differential equation, and the transfer function of the system is of first order as well. Let me give you another example, a little bit more complicated. Let's say. Now, the more or less the similar system, but this has an inductor in it. Let's see what happens to this system now. Again, we want to find the transfer function that relates VO to VI. Again, KVL gives us the following equation. The voltage input is VI, and the voltage drops are L di dt plus Ri plus 1 over C integral I dt. Okay. And VO is again 1 over C integral I dt. Okay. Taking the Laplace transform, VI of S is LSI plus Ri plus 1 over CSI. Okay. And VO is, what was it? 1 over CSI. Again, we can substitute I term or just divide VI over VS. The output voltage divided by the input voltage gives us 1 over CSI. This is like this, if you like. I terms cancel, and CS terms are collected together, and we get 1 over LCS squared plus RCS plus 1. Okay. So this system has LC and RC terms, as you see in it. These are the parameters. And this is a little bit like, this system is a little bit like a mechanical system, a second order mass spring damper system. Its transfer function is quite similar. Actually, it is a electrical analog of a mechanical mass spring damper system. Okay. There are other possible systems. I will give some examples. I'm not going. I assume you know these things from your electricity course, more or less. So I'm not going to spend too much time on it. But let me briefly give you one more example, and then we will go to electromechanical systems, which is more important for us. That is, electromechanical systems convert electricity to motion and vice versa. So we will look at a multi-loop example in which you will have not just one electrical loop, but two electrical loops here. So it is kind of similar to multiple mass systems in mechanics. Let's say that we have, this is VI, this is R1, C1. R2, C2 is here, and this is the output. All output is the voltage across the second capacitor. Let's say this is the current is I1 in the first loop, I2 in the second loop. This, by the way, this example is from the book by Ogata. That is this. Let me just write it here. This example is from. Why do we get this? I don't know. From. I could give it the page number. You might want to have a look at it. Oh, the page number is. If I'm not wrong, it's 204. So there are two loops, KVL for each loop. So this is loop 1, this is loop 2, as you know. And the first one gives VI is equal to I1 R1 is the drop. Now, as you see, the current goes, I1 goes in this direction, but there is an I2 which goes in the opposite direction. So this is gives you 1 over C1 integral I1 minus I2 dt. Yes, that's it. This is the first loop. The second loop equation gives you the voltage across next one plus I2 R2. We are tracing the following path like this, but this is negative plus 1 over C2 integral I2 dt is equal to 0. Okay, and the output VO, again 1 over C2 integral I2 dt is the output. Okay. So we take the Laplace transforms of these equations. VI is equal to R1 I1 plus 1 over C1S I2 minus I1 minus I2. This is the first equation. The second equation is uh, 0. Now, and the output VO is 1 over C2S I2. Now the trouble is the variables we need to eliminate are two here. We need to eliminate I1 and I2. Let's write it. We need to eliminate I1 and I2 to obtain a relationship between the input and output. We have three equations in our hands, so we can do it. Well, you can just substitute one to another to get that, but might be a quicker way. We can write, for example, the matrix equation like this, which is the following: R1 plus 1 over C1S. And okay, so this is a matrix equation. It can be solved for R1 and R2. Sorry, I1 and I2. So solve for I2. And then if you substitute the solved I2 into here, you get an expression for VO. Substitute solution for I2. Okay. How do you do it? This is a 2 by 2 equation. You can use Kramer's rule, for example, which is not too hard really. We just need to solve for I2, by the way. So if you want, you can do, for example, the Kramer's rule. I2 gives you the following determinant, R1 over R1 plus 1 over C1S minus 1 over C1S. We replace this by EI and 0 divided by this determinant of this whole thing. You know, it's a lot of algebra, but it is doable. And then you substitute this into here. And if you play with it a little bit, eventually what you are going to get will be the following. I'll just skip the intermediate steps. The G of S, which is the output divided by the input voltages, is equal to 1 over just a second. Plus 1. Okay. Excuse me for a second. I will be back in a minute. Okay. So this is the result is the transfer function, which is kind of looks complicated, but it's simply a second order system. As you can see, there is the S squared term as the highest S term. So it gives a electrical system of second order. For other systems, it is also passive systems. You can derive the equations quite similarly. It shouldn't be too much of a problem to derive the equations. As we have said, the electrical systems by themselves are, important, but for us, the more important thing is the so-called, any questions? Electromechanical systems, which are basically electrical motors and the generators. These are, the electricity and mechanics are coupled here. So it is coupled electrical plus mechanical systems. For example, the most important thing is the motors. Electrical motors are commonly used everywhere. But the reverse of the motor is the generator, which generates electricity. But there are also things like loudspeakers, let's say. They are electromechanical systems. Microphones. These are electrical systems as well. These generate sound from electricity or electricity from sound, microphone, for example. The whole idea is the following. If I give you a motor, let's say, a DC motor, the motor has a, voltage applied to it. There is a current going through the motor, and the motor's output is from a shaft, like here. And this shaft generates a rotation, let's say omega, angular velocity omega, and it also generates a torque. Now you see that V and I are inputs are electrical quantities. The outputs are mechanical quantities here. But these are sort of coupled in an intricate way. I'm not going to go into the details of how an electric motor works. It is basically because of the interaction of the electromagnetic field with the rotating motor, we generate the motion, as Faraday was able to show in the 19th century. But we are going to try to model the electrical motor as follows. This is the physical system, let's say, but the model we will be using, let's say this is V, what do I use, VI or V? Okay. The model we are going to use will be the following. The electrical motor has a winding that has a resistance of R. Okay, this is the resistance of the winding of the motor. And the winding has some inductance which we will model by L. This might be something very small, but still it might exist. Then the electrical motor is something like this, let's say, on both ends, and then this is the motor. With a shaft rotating, okay, and this shaft usually does not rotate by itself. It is usually connected to a kind of some kind of inertia or something, okay. The motor itself might have an inertia, but it usually works like this, okay. So I can kind of erase this part. So this is the motor. There is a current that goes through this motor, I. Let's say this is V, the voltage. The inertia, the polar moment of inertia is, let's say, is J. And this thing rotates with angular velocity of omega, and it generates a torque of T, as you see, okay? Okay, so this is the schematic of the model of the motor. There is something important in the model of the motor. There are two equations, the motor equations, so to say. You probably have not seen these before. That relate electrical quantities to mechanical quantities. One is the following. The torque generated by the motor is proportional to the current goes through it, okay? So the more the current goes through the motor, more torque it generates, okay? And a mechanical quantity, torque, is proportional to the current. Moreover, there is a voltage drop across the motor. So let's say that this is plus, this is minus. Let's call this VB. Let's call that the voltage drop across the motor as VB, and that is proportional to KE times omega, which is proportional to the angular velocity. As you remember, omega is the angular velocity, like measured in radians per second, and T is the torque in Newton meters, and KE and KT are constants. KT is called the torque constant. Obviously, these are linearized equations, and this is called the back EMF constant. These are static equations that relate electrical quantities to mechanical quantities. The torque is proportional to the current, and the voltage drop across the motor. This voltage drop is called, by the way, as I have said, the back electromotive force, back EMF, is Ke times the omega, angular velocity. Well, how do we derive this? This is kind of empirical, but also it has basis in the electromagnetics, okay? A current that grows through a magnetic field generates a force, and the motion in a magnetic field generates let's say, voltage difference. So these are the Faraday's laws of induction stated in another form, if you like. But I don't want to go into details of these. So this is the motor equations, but we are not done yet. These are the static equations. We have to write the mechanical and electrical equations, and the mechanical and electrical equations, as you see, will be coupled to each other. The electrical equation for the circuit of the motor is as follows. The voltage input, V, is equal to the voltage drop across the motor, which is Ri plus L di dt, plus the back EMF, Vb. Okay. Now we can write this as V is equal to Ri plus L di dt. That's okay. But Vb is now Ke times omega. We see that the electrical equation is coupled to the mechanical term, omega term, okay? So the rate of rotation of the motor influences the electrical equation. The mechanical equation states the following. We have an inertia rotating. The torque that is generated should be equal to J times theta double dot, right? Which is I times alpha in a way, is equal to the torque generated, and that is equal to Kt times the I. Now, theta, where does theta come from? Remember that theta dot is omega, and theta double dot is actually alpha, which is omega dot. So you can write this equation as J omega dot is equal to Kt times I. And we see that this is our mechanical equation. A mechanical term is equal to the electrical term. So the mechanical and electrical equations are coupled to each other. So these equations, as you see, are coupled, and their solution requires the solution of those coupled equations as well. Okay. I will take a break now for a while. I'll be back in about 10 minutes. Okay, see you. Okay, hello again. I guess I forgot to stop the recording, but let's continue anyway. Okay, so just a second. So let's share the screen again. So this is the equations that describe the system are coupled electrical and mechanical equations, such as this one and this one, okay? Two equations that are coupled. By the way, here, two things I have to mention. This inertia, J, might include the inertia of the motor also, okay? The motor itself might include that. Secondly, there might be some friction over here. Let's say viscous friction or something. In which case, you might add one more term to your equation. Let's say if there is viscous friction in the motor, somehow you want to model the energy dissipation. In that case, you would have j omega dot plus, let's say, bt times omega equals kt times I will be your defining equation, okay? Viscous friction, let's say bt is here. It is possible to have that. So in this case, our equation reads like this one. Okay? So this is equation A, and this is equation B. Two equations which are to be combined. As we know, what is our input and what is our output in this case? Our input for a motor is the voltage input, okay? Voltage V. And our output is, let's say, it is the quantity we're interested in, but usually it is the quantity we are interested in is the angular velocity. So it is omega. So we would like to obtain a relationship between omega and the voltage. So what we do is take the Laplace transform of A and B equations, and what we get will be Ls plus Ri, isn't it? Plus Ke times omega is equal to V. That's one thing. Secondly, j omega dot, so j s plus dt omega equals the torque. But the torque was given by, as you remember, kt times I. So let's use capital I here. Okay, so let's call it 1 and 2. And as you see here, the t term is already eliminated. Only thing is, I needs to be eliminated. Eliminate I. For example, we can say that what can we say? I is equal to so we can substitute that in here. Substitute this equation 3 to 1 will give us Ls plus R I is this one, Js plus Dt divided by Kt, right? Omega plus Ke times omega is equal to V. We multiply everything by Kt. And we get the following. Okay, so this thing, this thing that is in the bracket is the transfer function of this system. Okay, it's a second order transfer function, but usually the inductance of the motor is negligible. If the inductance is negligible, if L is equal to 0, this equation simplifies a little bit. Because in the motor, the inductances might not play a very big role. In that case, V over S, Vs over omega of S, the L terms drop here, especially the S squared term drops. And you get a rather simpler expression, Kt divided by JRS plus RBT plus KE, KT, which you can write, if you like, as JR plus JR. So it is a first order system, as you see. A first order system, a first order differential equation, which relates the angular velocity of the motor to the voltage input. Okay, it's a dynamic equation. Now, one more thing I want to do here is something very common, so I want to look at that, and it is the following. Again, we will look at a motor with gears. That is, a motor usually rotates at a very high angular speed. So in order to decrease that angular speed, we connected to before connected to inertia, we connected to a kind of a gearbox. So what I will be looking at now will be the following. First of all, we will assume that the motor inductance is zero, so it is kind of simplified. Now, the motor itself is connected to not to the inertia directly, but to a gearbox, if you like. Then this is connected to a large inertia J, and that is connected to a damping dt, let's say. So this is gearing with a gear ratio of n. This is, let's say, omega 1 and T1. This is gears, and this is omega 2 and T2. This is R. What else? This is V. The current that goes through is I. Okay. We will more or less follow the same steps. Let me just write the equations here. The electrical equation looks like IR plus KE times omega 1 equals V. Okay, this is the first equation. Then we have the gear equations. Omega 2 is equal to 1 over n omega 1. T2 is n T1. Okay. And T1 is KT times I, the motor constant. These are the gear equations, and this is the motor gear torque equation. Okay. And the mechanical equation looks like J omega 2 dot plus dt omega 2 equals T2. Okay, here I'm summing up the forces on this thing, on the second mass. But T2 is NT1, and NT1 is N KT times I. Let's say that this is our second equation. So, we take the Laplace transform of 1 and 2.
Hocam, can I ask a question?
Yes.
Hocam, while we were working on the gears types stuff, let's say, we were drawing reaction force in the gears, then we will make them like create a relationship between them. Why we just directly create a relation between T1 and T2?
Why did we create a relationship between T1 and T2?
Hocam Türkçe söyleyebilir miyim?
Efendim?
Türkçe söyleyebilir miyim hocam? Türkçe söyleyebilir miyim hocam?
Söyle.
Hocam normalde yukarıdaki gear ile aşağıdaki gear'da T1, T1 and T2 diye böyle bir reaction force'ları oluşturuyorduk ilk başta öğrendiğimizde. Şimdi oluşturmadık ya, onu neden yapmadık diye sordum.
Well, we describe the gear with these equations, okay? This is the gear equations here. n is the gear ratio, the torque is increased n times, the velocity is decreased n times. I have derived those equations when we looked at the gears. Now I'm just using them. I'm not deriving them anymore. Okay? You know, it would be a waste of time to derive them again. Do you understand?
Yes, hocam, thank you.
So we take the Laplace transforms. From the first equation, for example, we can say that I is equal to V minus K E omega 1 divided by R, right? From here. Which I can write as omega 1 is n omega 2, right? So V minus K E n omega 2 over R, for example. Which I will substitute into the second equation, which is the following. Js plus dt omega 2 is equal to nkt times I, and I, well, I should say I is in capitals, but I is here, so it is nkt times we have omega 2 in both sides and also V. We collect the omega 2 terms now, we can collect them. And what we get will be the following. Js plus dt plus n squared kt ke divided by r omega 2 is equal to V. So what we are really interested in is omega 2, the transfer function, which we will call, let's say, g of s, which is omega 2 of s divided by v of s is going to be nkt over r divided by again, this is a first order. This is kt ke. Don't be. This looks ugly. Let me write it again. Now compare this to the non-geared thing. We have the following. Here, everything was not divided to R. In the non-geared thing, we had well, this, and if you make n is equal to 1, actually, you get the same equation. Okay. There is one more thing. In this case, we have assumed that the motor itself, let's say, has negligible inertia. So, what if, let's say, it doesn't? So, motor has an inertia itself. The electrical part is the same. We have the motor as follows. The motor itself has a torque, but it has an inertia as well. And this is the gearing. I'd like to draw the gearing like this time so that you don't get confused. This is the second inertia. This is J2, this is J1, which is the inertia of the motor. This is the gear hand, okay? And here, the motor generates a torque like Tm, motor torque, and this is omega 1. So we don't neglect the inertia of the motor. Now we are just looking at the mechanical part, not the electrical part is more or less the same. I will just write equations for J1 and J2. This is a purely mechanical thing, but let's do it for the sake of completeness. For J1, we write J1 omega 1 dot is equal to external torque, which is Tm minus the gear torque, Tg1, let's say. This is torque. Gear torque minus dt omega 2. And by the way, this is omega 1. So this is omega 2. This is whatever Tg2 actually turns this thing. From the first equation, well, this Tg1 and Tg2 are related to each other by the gear equation. But I can write this Tg1 is equal to the motor torque minus the J1 omega 1 dot from the first equation, okay, which can be written as Tm minus J1 and omega 2 dot, okay. So I have eliminated omega 1 dot from our equation. And from the second equation, this is from 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 this equation, I can collect the terms together and so on. You have J2 S, let's say, plus ET omega 2 is equal to TG2. But TG2 is n TG1, and TG1 is n times this thing, Tm minus J1 n omega 2 dot. Sorry, I should say not dot anymore, but rather S times that. And S omega 2. Oh,
Hocam tekrardan bölüyorum da bir sorum vardı. Hocam benim sorduğum soru buydu. Burada mesela TG1 yazdık, TG2 yazdık ya hocam bu soruda. Önceki soruda neden yazmadık bunları? Onu sormuştum ben. Ya belki telaffuz edemedim. Ondan dolayı.
okay, because since these gears don't have inertia themselves, okay, TG1 is equal to T1 and TG2 is equal to T2. Okay, very simply.
If there is any inertia in between in the first row, so it needs to be TG1, right?
Yes, yes.
Okay, thank you so much. Hocam. Thank you so much.
So omega 2 terms can be collected together again. J1 and n squared S. Here you have J2. And what you get eventually, well, let me write this as NTM minus n squared, or J1 times n squared S omega 2. And if you collect the terms together, what you get is going to be the following. J1 n squared plus J2 S plus ET times omega 2 of S will be equal to n times the motor torque. So, in this case, omega 2 of S divided by T of S the equivalent inertia of this system is something like this. Or if you like, it depends, of course. Yeah, the effect of the inertia of the load becomes less important compared to the inertia of the motor. By the way, here we have derived the equation between omega and T, which is the torque, this is the motor torque, by the way, Tm. But you can also go on and derive the other quantities, such as the motor torque is related to the current in the motor and so on. But we have just looked at the mechanical part here. Okay. Any questions up to here? Let me see. Yes. Okay. So there are other examples of these in your book. And there are other things which I'm not going to go on to, which is the operational amplifiers and so on. So much for the mechanical systems, actually. This is as much as we will cover them. Are there any questions? If there aren't any, well, if there aren't any questions, I will go on with some other kinds of systems. Now we have seen that we could express mechanical, electromechanical, and electrical systems all by the same kind of input-output formalism in which you have the input to the system, like input, and output, and the transfer function multiplies them. Just a second. So that, for example, if the input is U of S and the output is, let's say, Y of S, okay, the transfer function of this system, G of S is output divided by the input, okay? So that the output Y of S is transferred to, well, the input is transferred to the output simply by this mathematical operation, that is algebraic operation. Actually, what this represents is a physical system, okay? Physical system with a certain differential equation. The nice thing about this formalism is this: if you have multiple systems in which you have one input, let's say U, then you have G of S, then you have, let's say, Y1 of S comes out, and this output goes to another system, let's say G2 of S, let's say this is G1 of S, and then this becomes Y2 of S, let's say, okay. In this case, the whole system can be combined algebraically without too much of an effort as follows. You simply have Y1 of S equals, let's say, G1 U, G1 U, or G1 of, let's say, S times U of S. Yeah. But then Y2 of S equals G2 times Y1 of S, as you see. Output, this second output is G2 times the first input. So you can write Y2 is equal to, or Y2 of S, I should say, function of, they are all Laplace transform functions. G2 times Y1, which is G2 of S times G1 of S times U of S. So the combined transfer function G of S is simply the multiplication of the individual transfer functions, G2 of S, G1 of S. The order of multiplication usually doesn't matter unless G1 and G2 are matrices, but usually they are not. So we have that property. Just a second. I'm looking for something. Okay. So we can represent systems by blocks, as you see, and it is possible to use the so-called block diagrams in order to represent systems. For example, a system has an input like U, you have a G of S, and output is Y. Now we can manipulate all these things in order to combine complex systems to each other. For example, you might use combine, for example, such systems. Let's say you might have one input to a system U, well, the same U might be entering here, by the way, and then we might be adding up these things. I will explain these, by the way. Let's call this Y. If you have two transfer functions like this G1 and G2, for example, you can write this as added up Y, well, I'm using this one, Y is equal to Y1 plus Y2, which is equal to G1 U1 plus G2 U2, well, G1 U plus G2 U, which I can write as G1 plus G2 U. Okay. So I can combine them with an addition, and we can also, since the both signals are U, I can take a branch from here and make this thing U. Now, in the block diagram notation, let me say block diagrams here, block. If you have a signal, these U and Y's are signals. And in the block diagram, signals do not obey conservation laws. What does this mean? This means that when I take a branch from this U and move it to another place, This U does not get divided into two, but it is, if this is a U, this is also a U. Okay. This is just a mathematical fiction we are using. It's not a physical thing. Block diagrams are not really physical. They represent physical systems, but they are not physical systems themselves. And the thing we do, the elements in the block diagrams are as follows. One is the, as you see, the blocks G of S. Second thing is the summing point in which two signals come. Let's say signal one, let's say A, and let's say this is B. And next to them we put signs, and one signal goes out, C. Okay, so this is a summing point, in which case we represent C is equal to, for example, C would be A minus B. Because A is positive, B is negative, there is a minus sign next to B. You have C, output C is equal to A minus B. If you have multiple signals like here, let's say S1, S2, S3, S4, let's say this is plus, minus, and let's say this is the output S5, you would have S5 would be equal to, for example, S1 minus S2 plus S3 minus S4. Okay, something like this. So summing point is one more thing. The third is quite simple, as I have said. The branch point, if you have a signal, if you take a branch from that signal, if U is a signal like this, the branch point also gives you a U. No conservation here. Branch point. So that the signal itself gets divided into two, but it doesn't lose its variable. It doesn't lose its value because it's branched into two. It is not like a flow. It is a signal. We can use these in order to generate models of systems. For example, as I have said, you can use two blocks in series like this, connected to each other. This is G1, this is G2. Okay, this is U, this is, let's say, intermediate X, and this is Y. We know that Y over U, which is G, the total G is G1 times G2, okay? So you can represent this as, this is equal to U and Y and G. Okay, so series transfer functions can be multiplied with each other. Then you have transfer functions which are in which the signals are added like this. Y, let's say this is U. These are added in a summing junction. Here, Y over U would be, as I have said before, G1 plus G2, okay, as we have done before. So by the way, there are also, you should show the direction of the signals by the arrows. Okay, one more thing is the so-called feedback. Well, that is not a new rule, but in the block diagrams, usually you go in the forward direction. For example, let me draw it here. This is U. Let's say this is G1. This is Y. Now you might use, usually you go from left to right in the forward direction. This is forward. But there are cases, actually in feedback systems, we usually take a measurement and feed it backwards. Let's say this is G2. This is backwards or in the feedback direction. Let's say this is Y2. The importance of this is that we can use this Y2 in order to generate our U. For example, we can use it like this. This is a minus. Let's say this is an R. This is a R, let's say plus. Y2 is minus, and this is Y. As you see, this is a G2, by the way. It doesn't look like it, but I can use feedback to influence the input to my system. Now, that is the idea in the control systems. We measure the output variable of a system, use it to influence the input to our system, okay? If you try to derive the transfer function, let me do that and I will stop. Let's say that R is the input, Y is the output, okay? This is the input, and Y is the output here. And there is a feedback. As you see, we start from Y is equal to G1 times U. Well, this is just a regular thing. But U is equal to R minus Y2. Now, Y2 is G1, R minus Y2. Y2 is G2 times Y. Okay, this one is not necessary. So we have a Y here, we have a Y on the other side. We have Y is equal to G1R minus G1, G2, Y. Y terms can be collected. Y times 1 plus G1, G2. So we have Y is equal to G1 over 1 plus G1, G2, R. And this is the general transfer function of the feedback system. Okay, the thing inside the brackets. So if I have an R here, what I have in this box as a Y, the reduced feedback system is G1 divided by 1 plus G1, G2. Okay, is the transfer function of the reduced system, or the transfer function of the closed, so-called closed loop system, or the transfer function of the feedback system. Function of the feedback system. As you will see, this 1 plus G1 over G2 will be an important thing when we study the feedback systems. Okay. So much for today. Let me stop the recording.